Hello everyone, I'm Disha Bharadwaj and today we'll be discussing a very important topic from analysis and design of algorithms called quicksort. So let's get into it. Quicksort is an efficient sorting algorithm based on the divide and conquer strategy. It is widely used due to its average case time complexity of O(n) log n, making it one of the fastest general purpose sorting methods. By partitioning arrays around a pivot and recursively sorting subarrays, it achieves high performance in various applications. Its in-place nature means it requires only a small amount of additional memory, which further enhances its efficiency. Quicksort's balance of speed and resource usage secures its place as a fundamental algorithm in computer science. Now let us understand the divide and conquer strategy. We partition the array by choosing a pivot, splitting data into two subarrays. And then we recursively apply the sorting process to each subarray independently. The sorted subarrays fit together naturally without any extra merging steps, as sorting is done in its place. Choosing the right pivot is very important. If we choose the first element as the pivot, it is simple but can degrade the performance on a nearly sorted array. And if we choose a random element, it reduces the chance of worst case scenarios and it gives good to average performance. If we choose median of 3, choosing a median of first, middle and last, it improves balance in partitioning. Poor pivot choices can lead to O(n) square time complexity, significantly slowing sorting. Yeah, so now let us understand the process of quicksort using an example. Initially, we have been given this array, and this is an unsorted array which we are going to sort using the quicksort algorithm. So basically here we are going to choose the first element, that is number 5, as our pivot element. And the second number, which is 3, we are going to assign the value I to it, and the last element we are going to assign the value J to it. So basically there are two basic conditions for quicksort to work. That is, we keep on incrementing the value of I till we reach a number that is greater than the pivot value, that is greater than 5. So as you can see in the second step, we are moving the I place of I from 3 to 9 because 9 is greater than 5. And the second condition is that we keep on decrementing the place of J till we reach a number that is lesser than the pivot number. So as you can see, J is at 4 now, which is lesser than pivot, that is 5. And now after we find two such elements, we are going to compare the index values of I and J respectively. So the index value of I right now is 3 and index value of J is 6. So our first main condition is this: if I is less than j, that is the index value of I, if it is less than j, then we are going to swap the values of I and j. So right now, as you can see, the index value, that is 3, it is less than 6. So in the next step, as you can see, we have swapped 4 and 9. We have swapped the positions of 4 and 9. So we keep on continuing the same steps, and each time in the next step you can see again there are new values of I and j. We are again comparing their index values, and you can see that again I is less than j, so we have swapped the positions of 2 and 8. Okay, and then again we continue. In the next step, as you can see, here the value of I is 8 and value of j is 2. Now we come to the second condition. That is, if index value of I, which is now 5, and the index value of j, which is now 4. So 5 is greater than 4. So that is index value, that is I is greater than j. So when this condition arises, we are going to swap the values of j and pivot. So what is the value of j? 2 right now. So we're going to swap number 2 with 5, our pivot value. In the next step, as you can see, 5 is over here and 2 is in the first place. Now once we have shifted the position of the pivot, okay, the left of the pivot we are going to consider as one array, and the right of the pivot element we are going to consider as the another array. So now we have two subarrays. Now we are going to recursively continue the same function, the same conditions. We are going to repeatedly check it until we find a sorted array, which is going to be from in like increasing order. That is 1, 2, 3, 4, 7, 8, 9. So that is how quicksort works. And also if you notice, the pivot 5 is placed in its correct sorted position. That we can tell because the smaller elements are to the left and the larger elements are to the right. So the elements which are smaller than 5 are towards the left and the elements which are larger than 5 are placed to the right of the array. So this is how quicksort works. Now, if we look at the performance analysis, we have the best and average case, that is n log n time complexity. It is achieved with good pivot choices. And secondly, the worst case scenario is it occurs when the pivot selection is very poor, leading to n square complexity. And for the space complexity, it requires log n space due to recursive calls on the subarrays. Now let's look at its advantages and disadvantages. Advantages, it is generally fast and efficient, performs sorting in place, reducing memory usage. Disadvantage is that the worst case performance can be very slow. Quicksort, it is unstable, meaning equal elements may reorder. And the practical benefit is that it often outperforms merge sort in real world scenarios despite its weaknesses. Now for the practical usage and optimizations. Number one, hybrid approach. Switch to insertion sort for small subarrays to improve efficiency. Randomized pivot. Random pivot selection reduces risk of worst time complexity. And lastly, wide adoption. Popular in standard libraries and systems due to speed and simplicity. These considerations help Quicksort maintain top performance in diverse computing environments. So thank you for watching the video till the end, and I hope you have understood the process of Quicksort completely, and please consider liking the video.